Welcome to the Kentucky Watershed Academy. I'm Steve Evans with the Kentucky Water Resources Research Institute, and in this session we'll be addressing hydrology and hydraulics as part of Module 2 for Water Quality Basics. In our overview to this module, we introduced you to the stream functions pyramid. In this session, we're going to look at the first two components of the functional pyramid, hydrology and hydraulics. At the base of the pyramid is the hydrology function. Hydrology refers to the study of the properties, distribution, and circulation of water on and below the Earth's surface and in the atmosphere. It encompasses precipitation, evaporation, infiltration, groundwater flow, surface flow, stream flow, and the transport of water and substances within the water. In relation to stream function, it addresses the transport of water from the watershed to the channel. Without surface water flow, there would not be stream channel formation and subsequent aquatic ecosystem. Parameters considered in the hydrology function of a stream include stream channel forming discharges, precipitation runoff relationship, flood frequency, and flow duration. Flow duration characterizes the ability of the watershed to provide flows of various magnitudes. Our second level on the functional pyramid is hydraulics. When conducting assessments or implementing a stream restoration project, it is important to distinguish between watershed scales of water transport, that's hydrology, and reach scale relationships that describe how water interacts with the channel, that's hydraulics. Hydraulic functions transport water in the stream channel on the floodplain or through sediments. It defines how water behaves once it reaches the channel and how it interacts with the bed, the banks, the floodplain, and the hyporheic zone. That's that porous sediment along and underneath the stream. It is closely related to geomorphology, that's level 3 functions, and many interrelationships exist between these two categories. At its basic level, water must be present in the channel before sediment can be moved. Hydraulic functions also affect many functions in the habitat and biology levels because they determine the amount of force and power that is exerted by the water on the aquatic habitats. We tend to look at streams as fixed features on a landscape where the water is always flowing. But in order to assess streams, we need to realize that they're always changing and think about that change in 4 different dimensions. Vertically, that's up and down. Longitudinally, that's the length of a stream. Laterally, side to side. And temporally, with time. Let's look at these in turn. Vertically, water bodies are not purely surface features, but are constantly interacting with groundwater aquifers, exchanging water, chemicals, and even organisms. Over its length, there are some portions where the water will flow out of the surface water body and downward into the aquifer, whereas in some of the lower reaches, it does the reverse. Water flows from the aquifer into the stream. Longitudinally, there are changes in slope and drainage patterns. Flowing water systems commonly go through structural changes en route from its source to its mouth. The slope and the topography of area will affect how the stream functions. Then we look at lateral. That looks at the channel and the floodplain features. So a stream has different parts to the channel, but it also expands out to the surrounding floodplains and hill slopes during floods. The entire gradient needs to be considered, realizing that a stream fluctuates laterally. And finally, we talk about that temporal change, that change with time. Streams are always changing. The vertical, lateral, and horizontal longitudinal structure is not permanent. So watershed managers should think in terms of the structural changes in progress and the rate at which the change is occurring. We've already spoken briefly about the hydrologic cycle and its elements in our overview. What we want to note here is how the precipitation, evapotranspiration, and infiltration affect surface runoff. Much of the precipitation that falls from the sky does not reach the ground where it can infiltrate or run off. Rather, it is released back into the air through various processes. These are known collectively as evapotranspiration. It includes inception, so trees intercept the precipitation as it's falling and then it evaporates from there. In transpiration, water is pulled from the ground through the roots, used by the trees, and then some of the water is released into the atmosphere through the pores in the leaves. And then finally, evaporation both from the soil and from the surface releases water into the air. So the amount of vegetation in the area affects the amount of groundwater and surface water. What precipitation does make it to the ground is drawn into the soil through gravity and capillary action. You know, that process that works upon paper towels to suck up water off a countertop. So this is pulling down through the pores in the soil. Soils with more porosity can infiltrate more water. Some are very compact and some are looser. After a storm, the water will travel lower with some of the particles holding water there as soil moisture. The maximum amount of rainwater that can enter a soil at a given time is called the infiltration capacity, and it's influenced by the soil type. Also, the structure, the moisture content at the start of the rain. Early in a storm, water usually enters a soil readily as it's literally sucked into that dry ground. As the soil becomes saturated, it becomes more difficult for water to seep into the ground, and so it's more likely to run off. Note that while moving through the soil, water will carry different chemicals with it into the groundwater supply, or some chemicals may remain attached to the soil particles. As water moves down through the soil, it will come to a place that is saturated with water, called the zone of saturation. This groundwater, if it produces a regular supply of water, it may be called an aquifer. Sometimes on the way downward, it'll encounter a layer of soil or rock that water does not move through very quickly. This is called an aquitard, and in this case it may cause a perched aquifer, as you see at the top, where the water reaches that and then will move along it laterally to be released in a seep. Or it may be confined within that layer, but you can see as that lower portion in the land surface that we call a stream interacts with the groundwater, it releases a flow to the stream. In areas which there are limestones and dolomite, karst topography may form from the dissolution of the rocks, creating sinkholes, caves, sinking streams, and springs. In some cases, the karstism will route water in a way that's very different from the direction of the surface drainage pattern. This can make it quite challenging to track the source of a pollutant that may be impairing a water body. If the rainfall rate is greater than the infiltration capacity of the soil, some water will run off of the ground surface. Runoff will also occur when the soil particles are completely saturated with water and cannot absorb any more. Different soils have different runoff rates based on the particle sizes and textures. In this example, you can have a soil with an infiltration rate of 1 inch per hour. You can see on the left, when the rainfall is 0.75 inches per hour, it's able to soak into the ground and there's not runoff. On the example on the right, the soil absorbs 1 inch per hour, but the remainder of that rainfall, 0.5 inches per hour, accumulates as runoff. We've seen that water will move down through the soil and the subsurface and move slowly towards the stream. When it surfaces at the stream, this results in a gaining stream, meaning that the surface flow is receiving supply from the underground sources. The groundwater is also joined at the stream by other surface flows, which includes overland sheet flow. So that's flow just running right off of the surface. 2, a subsurface flow through the saturated soil. And 3, a saturated overland flow, or a quick return flow, which emerges when the soil becomes so saturated that it has to release water back to the surface before it reaches the stream channel. As storms continue and the water table rises, then the saturated flow level moves further and further up the hillside. Streams may be classified as ephemeral, intermittent, or perennial based on their flow and its relationship to the groundwater table. Ephemeral streams flow for brief periods of time in response to a rainfall event. Because the surface flow is above the water table, these are called losing streams as the surface water is lost into the groundwater table. For intermittent streams, they flow during wet seasons, that is the winter or the spring, when the groundwater table is higher, but don't normally flow during the dry season when the groundwater table is lower. Perennial streams typically flow year-round. To illustrate this, in this figure we see on the top a higher groundwater table and on the bottom a lower groundwater table, and looking at a cross-section of the stream. So you can see the perennial streams on the left show in all cases the groundwater is moving towards the surface water. In intermittent, you can see when it's high water table, the groundwater moves towards the surface water, but during a low water table, the surface water is moving down into the groundwater system. And lastly, in ephemeral streams, because it's above the water table, flow is always moving downward into the groundwater system from the surface system. To look at this a different way, here's a side view. So you can see ephemeral streams are higher on the hill slopes. Intermittent streams are located in the middle portion where the water table fluctuates up and down. And perennial are located lower on the slope where, whether wet or dry season, the groundwater will move towards the stream. And lastly, we can look at this vertically. So you can see on our, looking from the sky in our watershed drainage, beginning at the outside, you're going to find ephemeral streams. Then moving closer downward, we're going to find the intermittent streams. And then finally, in the center there is where we'll find the perennial flow, where the water table is going to be located on the land surface. Urbanization of an area typically involves increasing the amount of impervious surfaces, or surfaces that don't allow water to filter into the ground. This includes paved surfaces, rooftops, sidewalks, and parking lots. An increase in imperviousness will decrease the evapotranspiration and infiltration, but it will increase the amount of runoff. Thus, urbanization increases the volume and velocity of water reaching the streams, but groundwater levels will decrease. The graphic here shows this phenomenon as the percentage of land area covered with the imperviousness area increases the amount of runoff. Thus far, we've been looking at the vertical dimension of the stream and how it changes. Now we want to pivot and look at the longitudinal dimension. 3 longitudinal zones are typically recognized. The first, zone 1, is the headwater zone. Here, flow is usually the lowest of anywhere else along the stream system. The slope is often the steepest, and erosion is greater than sediment deposition. In the second zone, the transfer zone, is the middle range of the stream where the slope usually flattens somewhat, more flow appears, and deposition and erosion are both significant processes. In zone 3, the depositional zone, this is near the mouth of the stream where the flow is the greatest, but slope is minimal and deposition of sediment significantly exceeds erosion most of the time. Erosion and deposition occur in all zones, but in each zone the primary processes are being emphasized. Headwaters need not be in mountains, but will vary in topography and by region. The shape of a stream will be influenced by the slope and geology of the valley in which the stream is located. Recognizing the valley shape will help to determine how streams in an area look, as the geology and topography will greatly affect the drainage pattern. So note, in the steep mountain valleys, the streams are confined, but will have a lot of vertical changes. In wide plains, the stream may be wide and flat. Not all streams are the same shape because they are located in different areas. Stream order classification assigns a number to a stream based on the number of tributaries contributing to its flow. Thus, it is a measure of the relative size of streams. There are different classification systems, but we're going to be looking at the Strahler stream numbering system. In this system, the smallest tributaries are referred to as first-order streams. The largest river in the world, the Amazon River, is a 12th order streams. The numbering works like this. If you have two streams that flow into each other with the same number, then it goes up a number. So two first order streams meet. What flows beyond that is a second order stream. Two second order streams flow together, that makes a third order stream. Now, if a first order stream flows into a second order, there's no change in the numbering that's there. In this classification scheme, first through third order streams are typically known as headwater streams. It's estimated that 80% of the world's waterways fall into this category. Fourth through sixth order are typically considered medium streams, although the terminology may differ somewhat. And seventh order or larger constitutes a river. If you were to walk from the headwaters of a stream down to its mouth, you would find that you would generally be going downhill, but you would also find some variations in the elevation on that walk. This is because the elevation moves up and down in elements known as a riffle, run, pull, and a glide. These typically occur in a sequence. A riffle is the shallow, faster moving area of the stream where the water is actually moving uphill just a little bit. A run is a medium depth area between the riffle and the pool pool is a deeper area with a low water velocity. A glide is the gradual increasing area between the pool and the riffle. So water energy is low in the pools where sediment will drop out, but will increase and even run slightly uphill over riffles and into the next pool. In this way the water will step down from a higher elevation to a lower one. These riffle, run, pull, glide sequences will help slow the water and releases the energy along these steep slopes. With some basics on the longitudinal changes in the stream, we now want to turn to the lateral changes in the stream. The stream channel has different parts. Looking here at a cross-section, we see the thalweg is the deepest part of the channel where the water will be moving the fastest. The scarp is the slope bank on either side of the channel. The wetted width is the area that has water at any given point. The stream channel extends upward to bankful, where it will spill out onto the floodplain. The bankful width is very important for understanding the stream channel. Relationships between the drainage area and the bankful cross-sectional area can be used to determine what the stream channel should look like in a stable environment. Streams may be incised too deeply to access their floodplain, or they may be over-widened. While water typically flows within the channel during base flow, it may extend across its floodplain in response to storm events. Some streams have a hydrologic floodplain, which is defined as being at or below bankful elevation. This area will be inundated in 2 out of 3 years. Then there's a larger area adjacent to the channel called the topographic floodplain. This area may be defined as maybe the 100-year floodplain or the 500-year floodplain based on the percent chance of reaching that level in any given year. However, because of probability, a house in the 100-year floodplain has 1% chance of occurring in a year, but a 26% chance of flooding within the term of a 30-year mortgage. A 500-year flood has a 0.2% chance of flooding in any given year, but a 6% chance of occurring over 30 years. This is kind of counterintuitive, so it's important to keep that in mind. Because of changes in climate, these percentages may be underestimated. The point is that water will interact with the area outside of the stream channel, and the water quality will be affected. This floodplain is important for allowing the energy of the stream to spread out across it during flood events to reduce erosion. Terraces may be present above the floodplain where the floodplain once extended prior to downcutting. That is the process of eroding and moving the stream downward in sizing. Further uphill will be upland slopes, which produce runoff or soil infiltration and groundwater. Under natural conditions, stream located on steep slopes may use a lot of up and down vertical variation in order to slow down the energy that's within a stream. But streams located on broader, flatter areas naturally will tend to move in a more sinuous path, lots of curves over that area. The sinuous stream with lots of curves, which are known as meanders, will tend to slow down the waters, leading to reduced energy and erosive force. When streams are straightened, this erosive force will increase as those bends are taken out. Floodplains will often have a variety of features which can help to slow runoff from the surrounding hillsides. They also can filter out pollutants, provide groundwater storage, and habitat. In this diagram here, we can see a number of features. We can see an oxbow lake where the stream once meandered there, but now it's been cut off, and so you have a lake habitat. You can see some meander scrolls. So again, areas where the stream used to flow through, but now that's disconnected. You can see a wetland back swamp or a splay that are there, as well as a natural levee. So these variety of features, again, provide storage, filtration, and habitat. Classification systems have been developed to help determine types of different streams. Dave Rosgen developed this classification system based on the shape of a channel, the longitudinal slope, and the ratio between the width and the depth, as well as entrenchment, sinuosity, and factors. So identifying stream types helps to predict the stream's behavior in terms of erosion potential, sensitivity to disturbance, and other factors. Stream types do not imply that any one is better than another. For instance, an AA plus stream is not better than a D, E, or an F stream. It's not like an academic grade that you receive. These are just variations of the type of channel that may occur in an area. Okay, now we want to pivot from the lateral dimension of the stream to the temporal dimension. We want to begin that by looking at the stream flow. The stream flow, or Q in this instance, is simply a product of the cross-sectional area multiplied by the velocity of the water that's moving through it. The roughness of the channel and the slope of the water will affect the velocity. For instance, if you have a lot of vegetation, that's going to slow down the water, and if you have a very steep slope, that's going to increase the speed of the water that's there. A hydrograph is used to show how a stream responds to a rain event. In a hydrograph, time is shown on the x-axis, and the stream discharge or flow is shown on the y-axis. In this case, you can see that the stream flow is shown through the pink line. Precipitation is also often shown on a hydrograph. This can either be at the top of the graph or superimposed, as in this case, with the blue bars representing the rainfall intensity. In the graph, you can see the hydrographic rise, or it's labeled the rising limb. This is when the stream is increasing in response to the rain event before it reaches a peak flow. That's the maximum flow during the storm event. The time between the peak rainfall and the peak stream flow is called the lag time. The receding limb is typically not as steep as the rising limb, as the floodwaters more gradually decline. You can see in this it's relabeled the recession limb. Finally, sometimes the base flow is graphed. Okay, this can be derived by connecting a dotted line between the base flow before the storm and the bend in the receding limb. This indicates the groundwater's contributions to the stream flow. Understanding a stream hydrograph is important because the sources of the water are different depending on when you sample, and this affects the water quality. During the hydrographic rise, most of the contaminants will be from surface runoff, and erosion will be present. During base flow, you will have more groundwater and see the effects from point source pollution. A stream hydrograph is a useful tool in visualizing the impact of urbanization on the stream flow. Here in this example, we can see that the same precipitation events produce very different discharges depending on whether the watershed has been developed or not. The pink curve shows the post-development scenario, and the dotted pink line, the pre-development scenario. So you can see that there are higher peak flows and that occur in a shorter time after urbanization has occurred. Stormwater infrastructure has been installed to move water off of streets, parking lots, and sidewalks as quickly as possible, routing it directly to the nearest waterway. Ditches, culverts, and pipes take water straight to the stream. Thus, we will see quicker, higher peak flows. The realization of the problems caused by this approach has created a new challenge for stormwater managers in urban areas. They now are seeking ways to slow down the water through storage so that flooding and erosion may be minimized. The installation of stream detention features allow these areas to function as a reservoir that holds stormwater and releases it slowly over an extended period of time. Because aquatic macroinvertebrates can be swept downstream when flows are excessively high, minimizing the flow levels that transport the sediments and aquatic organisms in a stream is important for maintaining healthy aquatic ecosystems. The shape of the hydrograph is not just affected by the amount of imperviousness, but also by the steepness and profile, as well as the shape of the basin. Try to think about how long it would take for individual drops of water falling at different points to reach the mouth of the watershed, and then put all of those drops together. This will help make sense of what a water sample represents. As a watershed coordinator, it's helpful to have a good awareness of the basic concept of how water reaches a common point. A really steep watershed will be expected to shed water quickly, causing a quick rise to the peak stream flow. The shape of the watershed will also affect the time that it takes for the water to reach a common point. So in graph A, we see here steepness. The first example has steeper terrain profile, producing quicker runoff and a more rapid increase in the flow or discharge. The second example has a flatter, more gradual stream slope, producing a slower, more moderated increase in the stream flow and rainfall event. The second graph shows differences in shape of the watershed. The first example, a larger area in the headwaters, results in some lag time in the arrival of the flow to form the peak. In the second example, sometimes double peaks can occur because the basin shape staggers when the flow arrives at the measurement point. And thirdly, narrower, more uniform area draining to the stream at all points produces a relatively small peak with a longer recession time for the waters. Understanding flow during a flood event is important, but so is determining flows during dry periods. Many permits will use the 7-day, 10-year low flow to determine concentrations that permittees are allowed to discharge. Also referred to as the 7Q10, it is the lowest 7-day average flow that occurs on average once every 10 years. During these low flow periods, less water is in the stream, and thus less dilution for pollution is occurring. In other words, pollutant levels may be more concentrated and likely to produce negative impacts when they're released during these time periods. To measure the various hydrologic and hydraulic functions occurring in a watershed, a number of measurements may be utilized by water scientists. In general, all watershed plans will need to have some understanding of the relationship between precipitation, runoff, and stream flow in order to calculate pollutant loading and interpret chemical sampling results. This is the hydrologic component. You could use stream gauges, models, equations to evaluate that relationship. The hydraulic measurements will help determine where and how much erosion is occurring and whether the high flows are impacting the macroinvertebrate populations. The interactions between the surface water and the groundwater may need to be traced in karst systems and may introduce unique flow paths. Basic awareness of the concepts of hydrology and hydraulic measurements presented in this short overview should help watershed coordinators to better understand the context for sedimentation, source tracking, and pollutant loading analysis.